Assalamualaikum warahmatullahi wabarakatuh and good morning. Today we are going to learn a new topic, continuous charge distribution. In this topic, basically we will learn how we want to study the numbers, the value of the electric field when you have a lot numbers of charge element on the surface. From previous lecture, we already understand the fundamental of electric force and electric field intensity. When then we have learned the relationship between the electric force, electric field, and the charge. Then we also already studied the concept of Coulomb's law, and we applied the Coulomb's law to solve several problems. Then we also already studied the superposition principle when you have to find out the net force when you have more than two charge interaction. In this lecture, we will understand the basic of charge density on the line, surface, and volume of materials. This new term for you, the charge density. Then we will evaluate the line charge distribution, surface charge distribution, and volume charge distribution. Charge distribution is known as collection of charge. When you have large numbers of charge, we call it as collection of charge. The particular charge distribution is known as discrete charge, or we call it as charge element. Distribution of charge along the line is called as continuous charge. When on the line you have a lot numbers of charge, to make it simple, the summation of charge, so we call it as continuous charge. Charge density means that the numbers is the numbers of charge element over the line or over the volume or over the surface. Charge element and the total charge due to this charge distribution. If let's say you want to find out the charge element, we use the formulation charge density times with the line element equal to distribution of charge density over the line. To find out the total charge on the surface, we use the integral of surface charge density over the surface area. Then if let's say you want to find the volume charge here equal to the integral of volume charge density over the volume. The electric field intensity due to charge distribution may be regarded as summation of field contributed by numerous points. So each of the charge element will produce the electric field. Then the summation of that charge element will give you the total electric field. For example, you see the formula for the electric field is constant K Q over R square. Let's say along this element you have a lot numbers of charge. Let's say you have a lot numbers of charge on the line. Lot number of charge here, we call it as, so for each element we call it dq. Here also we have dq and all is dq here. Each dq here, the charge element will produce this electric field, and this electric field from this q it produce dE, differential electric field. So dE, to find out the total electric field, so the E total here on the line equal to the summation of differential electric field. Equal to differential electric field, where to find here we have E equal to, so what you have here is, for sure you have summation. So summation we denoted by the integral K dq over R square. K dq over R square. Then from here you have dq. So you have distribution of charge dq. dq equal to, from previous we already stated that dq equal to charge density over the line for the case of this line charge. Then you substitute the value into this dq. Then you get the total electric field equal to the integral of rho L dl over 4 pi epsilon naught come from this K R square with the unit vector R here. For the surface charge, you have the integral of surface charge density over the surface ds over 4 pi epsilon naught R square with the unit vector AR. For the volume charge, you have the integral of rho v, so volume charge density inside over the volume over 4 pi epsilon naught R square with the unit vector AR. We look into first example. To find the electric field due to the line of charge, imagine that you have this ring. And from the ring, from the center of the ring, you have the radius R. Then the charge is distributed along this ring. Along this ring, you can see we have a lot of positive charge there. Each arc length given on the ring, we have given by ds. ds it places the quantity of charge that you want to measure. The linear density, so what we can conclude that the linear density, because here where is dq, dq is at this ring. So you have dq here. You have a lot of dq here. So to find the linear charge element, so you have charge element equal to, here is lambda, lambda here is line charge density over the times with the arc length, line density times with this arc length ds. This charge element set up differential electric field. Like I told you that it will set up the differential electric field dE. Also here it set up the differential dE. It comes from this charge element. So the differential electric field given by equation 1 over 4 pi epsilon naught dq over r square, or equal to 1 over 4 pi epsilon naught permittivity of free space times with charge density times with the arc length over r square. R square, what is the r square? R square is distance from this charge element to this point P. Using the hypotenuse, as you can see, we have this hypotenuse here. Using this hypotenuse, so you will conclude that R here is equal to Z square plus R square. Each contribute DE links at the angle theta to the central axis. The two perpendicular components cancel each other. So you know that the E element is combination of EZ and also the combination of ER. Electric field at the Z axis and also electric field at the R axis. So you can see we have here is DE, the resultant charge element. Then you also have DER at the horizontal axis, and also you have DEZ at this Z axis, the charge element along this Z axis. The two perpendicular electric field component will cancel each other, as you know that it will have opposite direction. The charge here will have opposite direction. So when you produce the charge, they produce the electric field, it will cancel out due to the symmetry. So from there, we can conclude that all around the ring, cancellation occurs because every charge element is symmetric partner. So here and here will cancel out also because of symmetry. Electric field from here and here also will cancel out. So these are all these charge element. Electric field produced by this charge element. The parallel component each have magnitude dE cos theta, because like you know that along this Z axis it form the angle theta. Let's say from this electric field produced by this, you have the ring, then the charge produced from here. So it will form the differential electric field. So relative to Z axis, we have dE cos theta. Cos theta, so using the hypotenuse, cos theta equal to Z over R. So cos theta, you have, let's say this is from Z, here is capital R, and here is R. So the Z, if let's say theta here, the Z equal to cos theta equal to Z over R. Then R here, when you convert, include this capital R term, so you have Z over Z squared plus R squared with the power of 1 over 2. Or you can say that the square root of Z squared plus R squared. Multiply with previous dE equation. So you have previous dE equation equal to 1 over 4 pi epsilon 0. Substitute the theta. It's like when you have the dE first. The first dE is equal to, we recall back, equal to, so I just put K here, K Q over R square. So R square, square root have also 1 over 2 there. Okay, 1 over 2 r square. Then because here you have to include the cos theta, so cos theta, you just put the value of cos theta, which is from here to here. After you substitute, then you can get this equation 1 over 4 pi epsilon 0 z lambda charge density over z squared plus r squared with the power of 3 over 2 ds. Okay, as huge number of these dE component is small, we set up integral that move along the ring. So small integral along this ring. So we solve for this charge element. So we have the arc length. The arc length produced from S equal to 0. Then we have, let's say the ring is like this. So you have a lot number of charge along this ring. So we have every arc length is given by ds, which ds means that the position of the charge element. So when you have s ds here, the integral along this ring, as you know that ring is starting from 0 degree. When it rotates, it will have 360 degree because of its round shape. So that's why here the integral is starting from 2 pi r. R means that we have constant radius 2 pi r from 0 to 2 pi r ds along this arc length. The electric field produced from this arc length, small arc length here. Then when we use the integral z lambda over 4 pi epsilon 0 in bracket z squared plus r squared with the power of 3 over 2 integral ds from 0 to 2 pi r. When you solve it, you get the total electric field equal to z lambda 2 pi r over 4 pi epsilon 0 times with z squared plus r squared with the power of 3 over 2. Make it simple when you want to include the charge term. So lambda 2 pi r is equal to q. So you have the electric field equal to charge times by z over 4 pi epsilon 0 in bracket z squared plus r squared with the power of 3 over 2. For a point that is you have z is higher than r. Let's say you have this z is larger than r is very small. So you can say that what it looks like the charge here looks like this point charge. It looks like this point charge because r here is approach to 0, very small, close to 0, very near to the center. So from here you have the electric field equal to 1 over 4 pi epsilon 0 charge over z squared. So here let's say this is this point source element. So what it looks like when it comes to close, so it just only move to this z axis. We looked into example 1. Figure shows a plastic rod with uniform charge negative Q. It is bent in a 120-degree circular arc of radius r and symmetrically placed across an x-axis with the origin at the center of curvature P of the road. In terms of Q and R, what is the electric field due to the road at the point P? So, in this case, you already given the angle here, theta 120 degree. You have the charge along the road, which is negative Q. Then you also have the electric field. Remember the equation for electric field. Electric field equal to constant times with the charge, total charge, over this r square. R square means that the distance from the point source to the applied point or received electric field. Because of its bends, it forms the angle 60 degree equally at the positive y-axis and also below y-axis, negative y-axis. Consider a differential element having the arc length ds and located at an angle theta above the x-axis. Let lambda represent linear charge density of the road. As usual, we have the element ds has differential charge of magnitude. So the charge element equal to the line charge density times with the arc length. So for each arc length, it produces the electric field. Each arc length will produce the relative electric field. Because it's negative, so it will pointing. Because here we have the charge here is negative dq. We have distribution of charge, so we have pointing to this. So we have two electric field component. First is Ex and also we have Ey electric field. Then each charge element produce differential electric field. So for each charge element, it will produce differential electric field. So differential electric field equal to 1 over 4 pi epsilon naught times with dq over r square, or equal to, when you want to include the term of line charge density, then the equation for differential element equal to 1 over 4 pi epsilon naught permittivity of free space times with lambda line charge density times with the arc length over r square. To find the electric field set up by the road, we need sum only the x component of the differential electric field set up by all differential elements. So we just only care when the electric field at the x-axis. Because as you can see, the y-axis, the differential electric field along the y-axis will cancel out with each other. So it will become, the Ey will become, which is the summation of electric field, potential electric field at the y-axis, then it will become 0. Then we just only care Dex, which is the electric field component at the x-axis. Dex equal to, it makes the angle theta here, so it produces dE cos theta. which is when you put into the theta term, we have 1 over 4 pi epsilon naught lambda r squared cos theta ds. And ds is because of this arc length, so we have r is constant. The only change here is for this arc length, we have r is constant. From this point, r is constant, but we have the only change is from, let's say from theta 1, it goes change to theta 2. So we just have the change of theta from point 1 to point 2. So ds equal to r theta r d theta. Integral the field over the angle from 60 degree to negative 60 degree to 60 degree. So we use the integral of 1 over 4 pi epsilon naught lambda r squared cos theta r d theta, because it is substitute from ds. So that's why here we have r d theta. Then we have lambda 4 pi epsilon naught r we can bring out, because why here we get r, because r here and r here can cancel out, so we get the magnitude of r here. Integral of cos theta d theta from 60 degree, negative 60 degree to 60 degree. Then when you solve integral of cos theta, you get sin theta. Substitute the value of sin 60 degree inside this theta, then you get the electric field equal to 1.73 lambda over 4 pi epsilon naught r. Because here remember that you want to get the electric field in this q and r term. You want to get the electric field in this q and r term. So you need to evaluate the lambda to change to the q term. Note that the full rod subtends the angle 120 degrees, so it's 1/3 of full circle. So you have 2 pi over 3, which is give you the value of 120 degree r. Because remember that the formula for this arc length is what? R s ds equal to r d theta. So your r is constant, but your theta is 2 pi over 3. 2 pi over 3 because it's bent with the angle of 120 degree. So that's why you have 2 pi over 3. Then substitute in this term line charge density. Line charge density, the formula is charge over the length. So you have Q over 2 pi R3, the arc length here. Then you get the equation 0.77 Q over R. Substitute into this electric field term, then you get 0.83 Q over 4 pi epsilon naught R squared. The direction of E is toward the road along the x-axis. Why it towards the road? Because the road have negative charge. So it let you know that negative charge will receive the electric field. Negative charge will receive this electric field. So that's why you have positive I hat. Positive I hat means that the direction, the unit vector along the x-axis. We look into the second example. Find the electric field E in this infinite line charge. So it's same concept along this line charge. You have this line charge. You have from point A to point B. You have coordinate here is 0, 0, z prime, and also you have coordinate here is 0, 0, z. Okay, to make it simple, you just assume that you have this kind of cylinder. You have this kind of cylinder where from this cylinder you have the line is inside this from the center. So from the center you have the radius from the center point, the radius to the end, to the edge of the cylinder we have the radius given by rho. Then you have several points, let's say several points from point B here. Then you have point A here. And here you have at the center of cylinder. Let's say here is the center of cylinder. From distance, from the center of cylinder, it makes going to the edge of the cylinder. It has the distance given by R. And it will make the angle here is from point, the angle from this produce the electric field at this point. Here we have the z-axis, and here you have rho. So you have the resultant differential electric field here is from dEz, and also it comes from dE rho. The angle made from here, so it make the angle of alpha. And then from point B to this point, the same point also it will make the angle of alpha 2. And then from point A, it makes the angle of alpha 1. Also, you notice that we have this kind of like hypotenuse. You can see here we have from Z prime to Z, we have the points of O to T. So here I can define that OT equal to Z minus G prime. And here we have, at this point we have rho, and at this point we have the R, and we have the angle here is alpha. It makes the angle alpha. Okay, and the coordinate at this point, they say the coordinate at this point P is x, y, z. It form the coordinate x, y, z. And here at z prime we have coordinate 0, 0, z prime. At this center, at this origin. And at this top we have the coordinate is at the top surface we have the coordinate at the top surface is 0, 0, z. Okay, let's try to solve the problem. The charge element dq associated with the element dl. So dl here, the line element we put equal to dz. Then you get the charge element dq equal to line charge density times with the line element equal to rho L dz. Then the total charge equal to the summation of charge element. As you know that the charge element you already convert to this line charge density term dz. The charge element we take from point A. The charge element we take from this point A to this point B. Because we want to know what is the point, the value of electric field produced to this point A and also produced by this point B. Okay. The electric field intensity at an arbitrary point. So the P here we have the coordinate is x, y, z, the coordinate at the point P. Then you need to find out the information you have is the vector r from this origin, from the center of the cylinder going to this point P. We have the value of the vector of r. So the r here equal to x, y, z, and minus the vector at the center is 0, 0, z prime. Coordinate at the center equal to x, x vector plus y, y vector plus z minus z prime, z vector. Because you find out this is the vector. What you solve here is the vector. So after you solve this vector, you put the term with the row term. So x and y equal to given by this cylinder row. Because here at the top surface and at the bottom surface, you have what you have here is x coordinate, y coordinate, and also you have x coordinate. Where the resultant here it form the radius row. Similar at the top surface also, it form the coordinate row. It form the coordinate row with the resultant from x axis and also resultant from y axis, y vector here. Then that's why here we have rho. Simplify the term, we have rho a rho, the rho vector plus z minus z prime, z vector. Already get the direction. To find out the magnitude, so you have r squared equal to, so you have x squared plus y squared plus z minus z prime squared, then you get the vector. The rho here, so you have rho squared plus z minus z prime squared, then you get the magnitude. Substitute into the unit vector form, so you have rho with rho vector plus z minus z prime z vector over rho squared plus z minus z prime squared with the power of 3 over 2. So this is your unit vector. Substitute into the electric field equation, then you get this term. Substitute into this electric field equation, you get rho L over 4 pi epsilon naught integral of rho vector plus z minus z prime z vector over rho squared plus z minus z prime squared with the power of 3 over 2 dz prime. Then you try to solve to include the angle, because right now is we have difference in term of angle from alpha 1 and alpha 2. So remember, we recall back the vector here, we recall back the figure. So we have position from the center of the cylinder, then it goes to point P, let's say from this Z prime. Then at the top here we have, so it formed the radius. So here from Z to P, from coordinate Z to P we have rho. Then we have Z to Z prime, we have connected by the Z axis. Then we have here Z prime to point P, we given by R. And we have the angle alpha here. So the angle alpha here, so when we find out in this hypotenuse diagram, so we have cos theta equal to, or cos alpha equal to rho over R. Rho over R, or at this point we given by the R here, capital R. So we have rho over R. Okay, because the angle is starting at this, taking from this point P relative to the top surface with the row of that have rho term. So that's why here we have cos alpha here. Then in order you want to include this to get in this R term, so you have brings this R here, rho over cos alpha, then rho over cos alpha 1 over, so inverse of cos alpha, you get rho secant alpha. Get rho secant alpha. Okay. Then your term here is equal to, your term here is equal to rho secant alpha. Then you want to solve for this z prime. You want to solve for this z prime. So z prime to z we have from 0 at the center to this point T. So we have z to z prime equal to z minus z prime. We can consider as OT. Then we make into this trigonometric term. So you have here is, let's say you have, assume that z to z prime given by OT. Then you have here is at the top surface the radius rho. This term from z prime to point P we just simplify by capital R. We form the angle alpha here. To make it simple, how you want to relate the relationship between OT and rho here. So you have OT over rho equal to tangent alpha. As we know that OT equal to Z minus Z prime, so you have OT equal to rho tangent alpha, so you have Z prime equal to OT minus rho tangent alpha. So differentiate this term, so you have dz prime equal, differentiate, so you have equal to negative rho secant square alpha d alpha. Okay, when you integrate dz prime over alpha, so that's why you get negative rho secant square alpha d alpha. Substitute, because our task is not finished yet, we have to find this electric field. Substitute the term here, then you have negative rho L 4 pi epsilon naught integral of, put the term here, dz prime equal to rho secant square alpha, rho a rho, so you have cos alpha rho vector. At the z vector you have sine alpha, so at the z vector you have sine alpha here, and here you have cos alpha, here over, you have rho squared secant squared alpha, which is here is give you information about this r. So that's why you have r squared, so that's why you have rho squared secant squared alpha. Negative, then you will integrate this term, you have to solve this equation. Then the electric field for the finite line charge equal to rho L line charge density over 4 pi epsilon naught over rho, recall back, this one is referring to the radius of the, from the center, then you have in bracket negative sine alpha 2 minus sine alpha 1 rho vector plus cos alpha 2 minus cos alpha 1 z vector. So for infinite line charge, where you have the coordinate 0 0 infinity, and at the point A 0 0 negative infinity, so you have let's say at this point A, z at this infinity, let's say from point B to z at this infinity, and at the point A z become, so this at the center, say at the center you have, then at the point from point A you have goes to negative infinity. So what will happen is it will form, the angle is alpha 1 will be pi over 2, and the alpha 2 will be negative pi over 2. When you substitute into this term, so you get the value of electric field for this infinite line charge, you will get rho L line charge density over 2 pi epsilon naught rho with the rho vector. Okay, or you can use later on, if let's say you use this Gauss law. With the Gauss law, you have the enclosed charge equal to E, the amount give you information about the amount of charge over the area. So you also can use this concept. Let's say Q also, it will give you information about this OL and this electric field. So the cylinder, you have the equation is 2 pi rho, the surface area on the cylinder. Then you have epsilon naught E at the end. When you substitute the value also using the Gauss law, you get E equal to rho L 2 pi epsilon naught rho at this rho vector. At this rho vector. Here when we talk about this rho vector, it form 90 degree at the top of surface. From 90 degree at the top of surface. We look into the electric field due to the charge disk. When you have arbitrary radius r less than smaller than capital R. So you just focus on the amount of electric field at this small r. Okay, assume that you just focus on the charge distribution in this small r region. The ring is so thin that we can treat the change on it as a charge element. So you have the charge element inside this R region. To find its small contribution dE to the electric field at this point P, so dE, the differential electric field, equal to Z dQ over 4 pi epsilon naught Z squared plus R squared with the power of 3 over 2. This is like equation for this line charge. Right now is you have the distribution of charge which depends on this the size of the surface from this small radius r to this large radius r. Because the ring is so thin, we call it as thickness given by r. Then we try to find out the charge element. We try to find the charge element on the surface equal to dq equal to this surface charge density given by lambda. So lambda here is surface charge density times with dA. Okay, you have dA there. So I just put here lambda is surface density. So dA is the area of the circle. So you have circumference given by 2 pi r. dA is the product of circumference and thickness. So circumference is, you have circumference is 2 pi r and thickness you have dr. It's like at the surface you have, on this surface you have this circumference and also the circumference is 2 pi r with the change of thickness here is dr. The change of thickness is dr. Substitute into this electric field equation. So you have electric field is the summation of small electric field produced by this charge element equal to delta Z over 4 epsilon naught. Because pi you already cancel out, so you have integral of Z squared plus R squared negative 3 over 2 to R dr. Okay, if let's say you want to know this equation, so let's say Z E equal to, we recall back E equal to, so I just simplify it, K constant Z over R squared integral of delta 2 pi r dr. So because you want to find the integral, the surface from point 0 to from the center to this r. So here is from center to the radius. The point outside radius. So you have electric field equal to kz over r squared integral of delta 2 pi r dr. Then from there you have, so I just bring out surface charge density because I don't want to have this, because surface charge density is constant. So I have k delta z r squared. So you also can bring out pi because pi is constant. Sorry, so I put in a proper way. So you have the electric field equal to k z, and also pi you can bring out because pi is constant, over r square. Then also you can bring out this delta also because delta is constant. Then you just have the integral of 2r dr. You have the integral of 2r dr inside here. Okay, so when you already have the equation of, so you can just elaborate the term, the constant term. So the k equal to 1 over 4 pi times with permittivity of free space epsilon naught. Then you have times with kz. So you have kz pi and also delta. So pi and pi you can cancel out. So what you have, the equation is k here, I'm sorry, k here, we no need to put k here anymore. So you have pi and pi you can cancel out. So that's why you have the electric field element, the summation of the electric field element is delta z over 4 pi epsilon naught. So here remember that you have, don't forget, we have z squared plus r squared negative 3 over 2. Where it come from? It come from here. It come from here, which is 3 over 2. After you include the unit vector, so we have here is 3 over 2. Okay, you have include this unit vector, so this one here you have 3 over 2. Then we brings out 3 over 2 here, so we have the integral z squared plus r squared negative 3 over 2 2r dr. So you setting up, okay, if let's say you setting up the things, okay, let's try. So let's say you already have z squared r squared with the power of negative 3 over 2 2r dr. So setting up, let's say z squared plus r squared is u. So let's say u equal to z squared plus r squared. Then you have du over dr. So your du over dr equal to r. So your du over dr equal to r. Then your du equal to r dr. Then you substitute into the term. I make it simple. So when you put into the term, so you get your E equal to your electric field equal to the callback. We have zeta 4 epsilon 0. Then you have integral of u with the term of negative 3 over 2 r dr equal to du. So you have du here. So easy for you to do the integral. So you have z delta over 4 epsilon 0 then do this integral, solve this integral. So you have u equal to negative 1 over 2 divided by negative 1 over 2. Then you just substitute the value of u. The callback u is equal to z squared plus r squared. Then you just substitute the value inside here, z squared plus r squared. When you substitute the value, solve this equation. Okay, when you try to solve this equation, you can try to do it. So here you get negative 1 over 2. Let's say you want to solve it, delta z over 4 epsilon 0. Then you have negative 1 over 2. You can have, bring it up, it become negative 2 over 1. So substitute the value is 1 over z squared plus r squared with the square root of z squared plus r squared. From, we take it from 0 to r. So here we can cancel out. So we just focus on to solve this term, because remember that here we have negative. So what you have here is, so I just focus to solve for this term. So I have z over, starting from 0, r from 0. So I have z squared plus 0 squared 1 over 2 minus z over z primes plus, because here I want to get positive term, so here we have negative, so that's why I starting 0 minus r. So here I get z squared plus r squared with this square root 1 over 2 here. Then z squared and z squared, square root of z squared. So here we can cancel out. So that's why z over z we get 1 minus z over square root of z squared plus r squared. So this is how we get this electric field. The final electric field on the charged disk surface. So we have del star 2 epsilon 0 1 in bracket 1 minus z over square root z squared plus r squared. Let's say r is going to infinity, and r is going to this infinity. So we just have delta over 2 epsilon 0 for infinite sheet of uniform charge. A point charge in an electric field is one of the application Millikan or drop apparatus. If they say you want to measure the elementary charge using, you can see we have the switch, and you want to measure, to investigate using the microscope, and also we have this battery to create the voltage to apply this electric field for this Millikan or drop. When a tiny oil drop are sprayed into the chamber, one some of them become negative, and either it become negative or positive. So because here we already applied the electric field on the surface. So that's why it becomes charging. Consider a drop that drifts downward through the small hole in plate P1 and into the chamber C. Then it will form the electrostatic force acting on charged particle located with the external electric field is F equal to Q electric field. This is one of the application of the electric field. There are several applications. If let's say you have time, you can go to this YouTube inkjet printer and also electric breakdown. You want to see what is the application of electric field when you want to print your paper, or you want to see how the electric breakdown happen in the power grid or in some of electrical device. We goes to the volume charge where we try to measure the electric field in this volume charge. Let's say you have this kind of the sphere, then you can see we have same concept. You try to, we have the point, source, and also the receive point. Here we have the angle. Let's say we draw this angle, this hypotenuse. So we have this hypotenuse is, can have this C here, R prime. Then we have position from this source point to this receive point given by R. And then also we have Z here. The angle here is alpha relative to the Z axis. Then also we have here the angle at this point, we have theta prime. Same concept, we have to check what is the component of electric field. First is the electric field is the resultant component of electric field at the Z axis, and also the electric field at this. You can see we have this small, let's say I assume that we have here is a small r. So here we have the component of DER. The charge dq associated with the elemental volume is dq, the total charge for the sphere volume. So we have volume charge density, rho v is volume charge density, and also times with the elemental volume, times with this elemental volume. Then the total charge in a sphere of radius a, so the radius here is given by a. So I put here the radius is a, so we have the integral of line charge volume charge density times with the elemental volume. So we have to integrate this elemental volume. We have 4 pi, the volume of sphere formulation is 4 pi over 3 a cube, because a here is the radius. So the radius for this sphere is equal to a. Then the electric field dE at the point 0, 0, z due to the elemental volume charge is rho v dV over 4 pi epsilon 0 r square ar. R square is the distance from point charge to this received charge. So we have this r from this elementary volume to this point. The coordinate here is 0, 0, z. Then AR, so what we can say that AR equal to the combination of cos alpha z vector plus sin alpha rho vector. Due to the symmetry of the charge distribution, the contribution to EX or EY add up, it will become 0. The only left is EZ because EX and EY, is, let's say, at the surface. So when it's distribution of charge on the surface, so here also you have EX and EY. So let's say we have, it will cancel out each other because of symmetry. So negative n and x, it will cancel out. Y and negative y also, it will cancel out. So what will happen is we end up, it become EY from the summation of differential electric field at this y axis, then end up it become 0. Similar to this x axis also, you will have AX equal to the summation of differential electric field at the x axis, then it also become 0. We just focus on what happened for this electric field at z axis. EZ, because we have EZ equal to E cos theta. So that's why we have the integral of dE cos alpha equal to rho volume charge density over 4 pi epsilon 0 permittivity of free space integral of dV cos alpha over r square. dV is the volume of the sphere. Using the volume of sphere, we recall back equal to r prime squared sine theta prime dr prime d psi prime and d theta prime d psi prime here relative to this cos alpha. Apply the cosine rule to get this equation. We recall back why we get this equation, because when you write up your drawing, you have this kind of drawing. R, then you have this, then you have R prime, and here you have Z. Okay, you have this kind of triangle drawing. So where is your score cos alpha? Your alpha cos is come from here. Using the cosine rule, so you have r prime squared equal to z squared plus r squared minus 2zr cos alpha, because it opposite to this alpha. How about this r squared? Because here you have the value of theta prime here. So the term expression for this r equal to z squared plus r squared r prime squared minus 2z r prime cos theta prime. Then we express this cos theta prime, cos alpha and sin theta prime d theta prime in term of r and r prime. So you get cos alpha equal to z squared plus r squared minus r prime squared over 2zr. Then you have cos theta prime equal to z squared plus r prime squared minus r squared over 2z r prime. Differentiate the equation cos theta prime with respect to theta prime. So you have sin theta prime d theta prime equal to r dr over z r prime. Substitute into this electric field equation. So you have this term. This side you take from 2 pi. This side, where is this side? This side it comes from this angle at the x and z, x and y surface. So you have this kind of angle. The change of angle here we have this side. Then you have dr. dr is from position of the source point to this. So you have dr, and also the radius here is given from a to 0, and then you have substitute the value because you want to get in this r term. So you have r prime squared r dr over z r prime dr prime. Then here, because you have cos theta term, so you have z squared plus r squared minus r prime squared over 2zr 1 over r squared. So here when you solve this equation, substitute 2 pi here. First you solve one by one. Solve for the easiest one first. So you solve for this term, so you get 2 pi here and 8 pi here. Then solve for this term. R prime in bracket 1 plus z squared minus r prime squared over r squared dr over dr prime. Then you solve this term, you get the electric field equal to q over 4 pi epsilon naught z squared at this z vector. Or somehow actually you can solve this equation using this Gauss law concept. You can do the practice how to solve this equation using the Gauss law concept. can apply using this Gauss law concept. Okay, you can do practice. I will give you the assignment later. So if let's say you not understand the topics, you can asking me. Okay, that's all from me for today. Thank you.